group that I'm largely not introduced to, so I'm excited to share some slides that may be new to you. Not new to me.
Hey, Bruno, would you like me to go ahead and start? Or just want to wait a couple of minutes to let everyone kind of keep filtering in?
Okay, we're live in YouTube right now, so yeah, you can introduce Stephen.
Oh, I didn't catch the end of that. You kind of broke up. Did you want me to go ahead?
Yeah, we're good. You can introduce Dr. Ryan.
Cool. All right. Hi, everyone, and welcome to the September edition of Life RCN Seminar Series. We're excited to have you all with us today for Dr. Steve Vance's presentation on the habitability of icy ocean worlds from a geophysical perspective. Dr. Vance completed an undergraduate degree in physics at UC Santa Cruz and pursued a PhD in geophysics and astrobiology at the University of Washington, Seattle. He has completed 2 postdocs, one as a NASA postdoctoral fellow and another at Caltech. He is currently a research scientist at the Jet Propulsion Laboratory of Caltech, and he is also the co-chair to the Europa Clipper Habitability Assessment Board. And with that, I'll pass the torch to Dr. Vance and let him take it away.
All right, Ross, thanks for the torch. Nice to be here and see everyone dialed in, and I guess to be broadcasting this on YouTube. So thanks everyone for listening. I take it this is an audience that's less familiar with ocean worlds, and so I view it as my responsibility to give a bit of an overview of that field, at least from my perspective, and I hope that I can then jump into some of my research. Usually I encourage the audience to, jump in and ask questions, and it's easier for me to gauge the audience's grokking of what I'm saying. So I guess in this case, I encourage people to do so if they feel comfortable, but also, any emoticons you want to throw up are also welcome. Okay, let me go on and share my screen here. Sharing my screen. Okay. And presentation. So I'll just look for a thumbs up to say that you can, you're seeing the right screen. This should be a full screen. Thank you. Yeah, so the theme of my work is trying to understand the interiors of ocean worlds. So what's shown in this pie here, and can you see my cursor?
I can on my end.
Okay, I see another thumb as well. Thank you. Okay, yeah, so interpreting the interiors of ocean worlds where we believe that there are subsurface oceans. We have pretty good evidence in a lot of cases. To understand more about their structure and composition, and thereby to understand their habitability. And most recently, I'm working on magnetic properties. And as you might have seen in my abstract, that's a area of active focus for us. So let me walk you through some more introductory material here. So ocean worlds in our solar system, we know of a few which span a range of sizes. And so here I'm showing a view of Earth with all of its surface water rolled up into a sphere. So we have a good estimate of the volume of water in Earth's oceans. And so we can imagine stripping the Earth of its water. The USGS generated this image, and then my colleague Kevin Hand was inspired to take that and compare how much water we think is liquid in Europa, the moon of Jupiter, which is roughly about twice the amount in Earth's oceans, which is pretty impressive for a moon that's about the size of our moon. But so Europa was kind of the start of our insights about ocean worlds, with good evidence for an ocean there being provided by the Galileo mission in around 2000, along with a lot of other circumstantial evidence. Since then, we've come to appreciate that Ganymede, the neighboring moon just a little farther out from Jupiter, also probably has an ocean. The amount of water, whether it be ice or liquid, is probably 25 times that on Earth, which to me is pretty amazing, and it's a much different world in terms of its similarity to Earth than Europa. And also we've learned that tiny Enceladus, shown here to relative size, is also likely an ocean world with a large proportion of its interior being composed of water, much of that in liquid form. So this new insight gives us some extended view of the idea of the habitable zone. There's understandably a big push in the rapidly growing discipline of exoplanet studies in looking for Earth 2.0, that is planets that are in the habitable zone of their star, which that habitable zone distance varies as a function of the type of star. And I'm excited about learning more about those types of worlds as time goes by. You might have seen the headline last week about a forthcoming paper. It's on archive of JWST discovering a world, an Earth-like world that seems to have dimethyl sulfide in its atmosphere. So beginning to get hints of possible biosignatures. Meanwhile, we can think about what's probably a much more prevalent type of world, that is an Earth, ice-covered Earth, or a watery Earth beyond the snow line. And the discovery of subsurface oceans around in moons orbiting large bodies gives us some inspiration to think about what those worlds might be like by studying ocean worlds that are different from Earth. So lots of exciting developments that cause us to imagine how life might have evolved differently or at all in those worlds. And for this group, I'm curious what ideas that might generate in terms of how life, if it developed in those worlds, might then transition to being multicellular. But the thinking about these worlds has to be done much more simplistically because we just don't know that much about them. So here's an example of the ways that we think about them. We do have constraints on their size and mass, which gives us then their bulk density. And we can plot that as a function of radius. So this is from a paper from Huisman 2006, one of the first comparative planetary science papers looking at many different possible ocean worlds. And so you can see that Enceladus clusters along with its neighboring moon Mimas, which looks like the Death Star, and Uranus's moon Miranda, for being small bodies, basically the density of water. And yet we know Enceladus now has a global ocean. And then we can go out to slightly larger satellites. None of these show strongly established evidence for an ocean, though Dione seems like it might be. Pluto's neighboring moon Charon may have had an ocean at some point. We can go out farther to larger objects that are still mostly close to the density of water. And Pluto seems to be an ocean world as well. And then I mentioned Ganymede. It has siblings, Callisto and Titan. These are remarkably large objects, again, close to the size of the planet Mercury. And so at the base of their ocean, we expect to have high pressure ice, which makes them just really interesting and weird to think about. And again, we can imagine them as analogues to Earth-like ocean worlds. For example, if we imagine a 100-kilometer deep ocean on an Earth-like body, that would also have high pressure ice at its base, most likely, and would have pressure conditions at the base of its ocean similar to those at the bottom of Ganymede's ocean, or Ganymede's water layer. Europa, meanwhile, is remarkably dense, more similar to the moon and its neighboring moon, and Europa's neighboring moon Io. And so something has happened with Europa. It's one of the reasons we think Europa is sort of special, and why I'm excited to be part of the Europa Clipper mission. It was mentioned at the beginning that I'm co-chair for the Habitability Assessment Board, which has the job of thinking about how all the different measurements of Europa Clipper combine to allow us to understand Europa's habitability. And I'll explain why we need to combine all those measurements as I go through this talk. Okay, so these are worlds with conditions like Earth, but different in a lot of important ways. Mainly, we can think about how these worlds vary in properties as a function of distance from the sun. So this is just some fun graphics from Wikipedia. You can zoom out from our neighborhood. You see Jupiter is already far away from the Earth, separated by this asteroid belt. Lots of small objects clustering in the vicinity of Jupiter, trapped in its Lagrange points. And And even farther out beyond the conventional solar system, we have this Kuiper belt with tons of objects, Pluto being one of these dwarf planets trapped beyond Neptune. And even farther out, we have even more objects like Sedna. So there's a whole host of possible ocean worlds out there. And again, their properties, their composition is going to vary with distance from the sun. Even farther out, we have this constellation of probably hundreds of thousands of objects that constitute the Oort cloud, a quasi-stable set of objects that sort of demarcate the boundary of the gravitational influence of the sun. Okay, so going out then as a function of distance, all the way out to the Oort cloud, you're going to have a condensation of more and more volatile materials, such that beyond or out at Jupiter, you definitely have water condensing as evidenced by these icy moons. But you get out to Saturn, and then you have methane and ammonia being stable at the surfaces. And out at Uranus, you have oxygen being stable at the surface. And then out at Neptune, you have nitrogen being stable. So you can see that the bulk compositions of these objects are going to be different. And so where there are oceans in the subsurface, the proportions of volatiles in the oceans are going to be different as well. So you can imagine taking the geochemical cycling that we know of on Earth and having that apply in different ways in these different objects. It looks like someone has drawn on my screen. That is not something that I did, as far as I know. I'm not sure if we can remove that. If you want to keep drawing on the screen, I guess that's fine. Yeah, it's kind of funny. Okay. I don't think I did that. No. Okay, so yeah, drawing this in schematic, I did this so that we can just imagine the scales of distance or length that are involved just radially, going from the top of an object toward its core. Earth has an atmosphere with a scale height of 100 kilometers, an ocean that's an average of 4 kilometers deep or so. So we know the atmosphere on Earth interacts with the ocean, mixes stuff up. We know the ocean is mainly sodium and chlorine, but that probably has to do with the complicated interplay between chemistry at the seafloor, possibly also chemistry at the continents, also the bulk composition of materials that form the Earth. And we know that the thermal conditions in the Earth's crust lead to a likely depth of water percolation of about 6 kilometers. So these are characteristic scales that determine the water-rock ratio of interaction, and thereby the kinds of materials that are present. And the fact that we have volcanism in the seafloor means that we can have exhalations of concentrated reductants, including iron and hydrogen, methane. So these are open questions whether those things also appear in places like Europa, where we don't know what the ocean composition is. We're beginning to have some constraints based on surface composition from near-infrared spectra. Europa doesn't have an atmosphere. It has an exosphere that is non-collisional molecules bopping around at the surface. It happens to be dominated by oxygen because Europa's ice is highly irradiated, and the radiation breaks apart the water at the surface, and oxygen preferentially sticks around because it's heavier than hydrogen. And we have evidence of possible brines underneath the surface of Europa based on Europa's complicated geology, as hinted at in this low-resolution image where you see all this reddish material and this remarkable lack of craters. And we are just beginning in the last 20 years to think about what ocean circulation looks like in these objects. And what I'm showing here is perhaps a somewhat antiquated view of how the ocean might work, stimulated by the question of whether some of these destabilization features at Europa's surface are driven by warm plumes rising through the ocean that could possibly be contained by Europa's rotation. These are so-called Taylor columns. And this kind of dynamic might exist, but it's likely that there's also a lot of turbulence in the ocean and lateral convection that happens. So possibly in the coming decade, we'll come to understand more about how these things work. And I've just listed some references here from the last 20 years or so. And unfortunately, some antiquated numbers here. Neveu et al., I think that was 2014. Moving on to larger bodies, Ganymede, Callisto, and Titan. We can ask, how dissolved materials in the ocean affect the structure and habitability? With these larger bodies, where the ocean thickness is on the order of 1,000 kilometers, pressures are so high at the base of the ocean that you end up with the possibility of high pressure ices, which are then going to affect the ocean chemistry, possibly in profound ways, possibly not, based on recent progress. This is all thinking about things in a radial sense, just going from the top toward the core. On Earth, we know that the system is much more complicated. That atmosphere-water interaction that I mentioned takes place with mediation from the continents. We have seafloor spreading and all kinds of weathering and mechanical breakdown due to ice sheets, all kinds of different things happening that we don't know a lot about for these other worlds, just because they're covered in ice and we haven't investigated them in detail. And so the other aspect that is implied here is one of time. And so how has habitability, we know that habitability on Earth has changed through time. That is, the type of life that is supported by Earth has changed in time. This is evidenced even just from the presence of oxygen in the atmosphere over time, going from an anoxygenic photosynthesis a long time ago, 3.7 billion years ago, and the rise of oxygen that was deadly to those first organisms, but they managed to make to make it work, and to the presence of oxygen today, that's notably and interestingly lower than it was just after the Cambrian explosion. By some measures, Earth might have been super habitable for organisms like us some time ago, but perhaps that caused its own problems in terms of fires and such. So lots to think about in terms of what life might be like, what the evolution of life might be like, what habitability looks like over long periods of time in these worlds. So just focusing in a little bit then on Europa, I want to share some slides that I like to show motivating the Europa Clipper mission that I'm involved in. And providing a little more perspective on this system. So here are the Galilean moons of Jupiter. I showed these previously. These are our best global maps after the era of the Galileo spacecraft that crashed into Jupiter in 2003. 400 years previously, in 1610, Galilei, the namesake for the Galileo spacecraft, scribbled this drawing of what he saw through his telescope when he first documented viewing of Jupiter, and its moons were critical in his overturning of Copernican theory, that put Earth at the center of the universe. And so we've come a long way in that time, and we've come to understand that these are worlds in their own right. That Io is volcanically active, more so than Earth, and people are actively watching the volcanoes at Io's surface and learning more about them. And we've learned that Io, Europa, and Ganymede are in this complicated dance called the Laplace resonance, in which they orbit in a resonant fashion, with Europa having one orbit for every 2 of Io, and Ganymede having 1 orbit for every 2 of Europa. And that coordination between them causes a forced eccentricity that keeps their orbits from being circular and causes them to be tidally deformed by the changing gravity of Jupiter due to their varying distances from Jupiter. And so that's what causes the volcanism at Io, and we expect that that's what keeps Europa's ice young, as evidenced by, again, the lack of impact craters that are seen on Ganymede, and even more so on Callisto, which seems to have a surface age of about 4 billion years. And Europa's surface indeed is altered at every length scale. So you see these fractures at a global scale are fractal. That is, as you zoom in, you see even more fractures. So fractures upon fractures. And we expect that these fractures, one compelling model for how they form is that you have opening on the tidal cycle of 84 hours. And And so you have this opening that then squeezes material onto the surface, and over successive days, that leads to these bands that are roughly 20 kilometers in length across them. And so again, you see this process repeating on multiple different scales, which suggests the ice has moved around to position these fractures optimally over where the maximal stress occurs. And so you have this picture of this globally active ice shell mediated by tidal flexing. And in places that tidal flexing and the dynamics in the ice that are yet undetermined, again, have led to complete destabilization of the ice. So here you see those linear fractures preserved in blocks of ice that have moved around in this chaotic matrix, which gives the name to these chaos regions. And we also see that the reddish non-icy materials, as identified in infrared spectra, are correlated with that destabilization, just as they're also correlated with these linear fractures where materials seem to have come up from underneath. Again, there are only a few impact craters on Europa, and where they exist, you see these rays of material. We're curious what that material contains, what it might tell us about the impact features. Again, you see that discoloration where the impact is. We also have these lenticulae, features that may be associated with some of the linear features. Some have suggested that these might be related to subduction, that is pushing of plates underneath other plates, which would be analogous to plate tectonics on Earth, that give rise to the movement of volatiles upward in Earth's crust and lead to some of the volcanism we see, for example, along the Sierras in California. And so that's some really exciting geology that we've gotten from Galileo and to some extent from the previous Voyager missions. From the flybys of Europa, we also got a sense of the interior gravity that has allowed us to infer the density structure. So one plausible model for Europa's interior structure is that it has a hydrosphere between 80 and 170 kilometers thick. And so again, the pressure conditions are such that you would then expect to have a seafloor directly in contact with the rock. And depending on the composition of the rock, the amount of iron present, and the error bars in the inferred gravity structure, there may or may not be a metallic core. So there's been some recent work on different assumptions about how Europa formed, how hot it formed, and whether it was hot enough to separate out metal and move the denser metal to the interior to form a core. And that's important in terms of understanding the iron content of the remaining rock, and thereby what types of water-rock interactions occur and what materials might be available to support life. So a little bit about how we infer the presence of an ocean. The most compelling evidence for an ocean also came from geophysical measurements, with the gravity providing some sense of the interior structure. Knowing that there might be liquid here, one can ask, is there liquid present today? And the way that you do that is by measuring the magnetic field in the vicinity of Europa. And so this is a depiction of Jupiter's very strong magnetic field, about 60,000 times stronger than Earth's. So showing the north pole of the magnetic field and the south pole down here, and the field lines wrapping around as dipole fields do. You can see in this illustration that the field is tilted by about 10 degrees. It happens that Jupiter's magnetic field rotates at about 10 hours or 11 hours as seen from Europa, since Europa's orbiting Jupiter. And so what the Galileo spacecraft observed, or seemed to observe, piecing together about 4 close flybys, is that Europa generates its own magnetic field in response to what it sees as a changing direction of magnetic field from Jupiter. So you can see that the North Pole and then the South Pole sweep through Europa. So now the North Pole is in there, and now the South Pole. So that changing direction due to the tilt of Jupiter's field leads to a strong induced field response. So a changing field in a conductor creates an induced magnetic field. And so that's the most compelling evidence for an existing ocean today, because the observed field is best explained by conductors near the surface, namely a salty ocean. And so, in fact, it seems to put some constraints on the lower bound of the conductivity of that ocean and thereby on the salinity. So we'd like to follow up and get some more details about that. Just because I have a nice image here, I want to elaborate on the tides that I mentioned. So again, there's this forced eccentricity, so a non-circular orbit, which then shown in exaggeration leads to stretching of Europa and thereby heating in the interior. And so some of the discussion among the geophysical community is, where is the heat deposited? That is, what is the rheological structure? How squishy are the materials in Europa? Up until recently, the assumption has been that most of the heat was generated in the ice, depicted qualitatively by the red here. More recently, work doing three-dimensional modeling of Europa suggests that you might actually have quite a lot of heat generated in the rock as well at the mid-latitudes, and possibly sufficient to generate ongoing volcanism even today. So more work needed, and possibly further close flybys of Europa to measure its gravity field can reveal how that could work. Okay, so advancing, since I have about 20 minutes left, I'll skip some of these slides. Just mentioning there's a range of impact structures, some of which are large and don't have any central features, and possibly indicating that the impactor punched all the way through. In general, the dynamics of these craters, how they formed, how the ice evolved afterward, could provide clues into the nature, the rheology, the structure of Europa's ice. I mentioned possible subduction, just the idea that parts of the ice might be subsumed into other parts of the ice, but before the ice equilibrates, that could end up with a feedback that drags the ice forward, similar to subduction on Earth. Okay. Convection in the ice is a possibility, possibly related to that subduction. But generally, if the ice is thick enough, you would expect it to have a high Rayleigh number. That is, like any fluid, if it's warmed from below and cooled from above, you should have density dynamics that cause the ice to overturn. Whether that can be sustained over long periods of time is not known. So all of these things cause us to ask, does Europa have the ingredients for life? We have good evidence for water, and we expect that because the water is in direct contact with rock, that we have all of the essential elements, the schnapps needed for life, and because of this geological activity, again with possibly oxygen being subsumed into the ice and deposited into the ocean, possibly hydrothermal activity, we might have chemical energy that could support life. And the fact that it's been simmering for 4 billion years, it seems likely that there was more tidal heating and more, thereby more geological activity earlier on. Europa's habitability could have changed through time. There could have been more chemical energy before than there is now, or it could have oscillated and changed through time because of the complicated exchange of energy between the moons through the Laplace resonance. So all of that begs the question of whether there might be hydrothermal vents, such as observed on Earth. This compelling imagery of organisms feeding more or less independently from the sun on chemical energy spewing from rocks. And oceanographers are discovering more and more of these types of fields, hydrothermal fields on Earth. And I can't promise that we'll discover these sorts of things in the near future at all in Europa, but wouldn't it be exciting to do that at some point? What we can do is try to look for signatures of strong energy input into Europa's interior. And so to do that, we have the Europa Clipper mission set to launch next year to investigate Europa's ice shell and ocean, its composition, its geology, possible current activity, namely possible plumes coming from the ice, and to do reconnaissance for future missions that might land on the surface. Here I'm showing some of the highest resolution imagery. So to do that, we have a suite of instruments for remote sensing from the UV through the visual spectrum out to the thermal, the near infrared, again, for chemical fingerprints, including organics, and active radar sounding, possibly to peer all the way through the ice and figure out the thickness of the ice, how the ice varies, and to some extent what its rheological and compositional structure are. In addition, while flying by Europa, we'll be able to sniff the atmosphere with a gas mass spectrometer for neutral particles, and with a dust analyzer for materials sputtered from the surface. And we'll have a very capable plasma and magnetic sensing suite to figure out in detail the magnetic induction that I described before, much greater detail than the Galileo mission did. And lastly, through dedicated radio tracking for the entirety of our every flyby of Europa, we'll be able to measure tidal flexing and get details about the interior structure. So the spacecraft is a solar-powered spacecraft. Here we show the radar antenna attached to the solar panels, and all of the instruments are together in this vault to protect them from Europa's radiation. We have the in situ instruments pointing forward to sweep up material from Europa as we're flying by, and all of the optical instruments, the instruments that do remote sensing, pointed downward for nadir sounding as we fly by Europa. And so the concept for the mission is not to orbit, but to fly by Europa about 50 times during the prime mission. And so here we're just showing the individual flybys of Europa, with the red coloration showing the closest flybys that are as close as 25 kilometers above the surface. And so we're going to build up detailed maps of Europa's surface, missing only a little bit at low resolution at the parts of Europa that are pointing either toward or away from the direction of Europa's orbit, the so-called leading and trailing hemispheres. And so we do a multiple flyby mission in order to stay out of the intense radiation environment at Europa. Just like the Juno mission, we'll have a highly elliptical orbit that will allow us to swoop in every 2 weeks and build up our map of Europa. First on the anti-Jovian side, the side of Europa that's facing away from Jupiter, and then with a 6-month break, returning to Europa, looking at the sub-Jovian side, and with each flyby, increasing our accumulated radiation dose, but during the prime mission remaining below our target of 3 megarad of radiation. So this is just showing the different phases of the orbit. You can sort of see how the parts of the orbit that go by Europa also precess in where we're sampling Europa's orbit. So we're going to get a good sampling of the overall orbit of Europa in terms of the both the sampled orbital trajectory relative to the sun, and also relative to Jupiter's rotation. So briefly, the instruments are all delivered and now assembled onto the spacecraft. That includes the in situ instruments, just showing some nice pictures of the hardware that's been delivered, and the remote sensing instruments. These are now on the payload. I encourage you, especially if you're already on YouTube after this talk, to search for Europa Clipper live, and you'll get a view of Europa Clipper in the high bay at JPL, where as it's currently being tested. I believe it will be there for the next month before it goes up the hill for further testing before shipping out for its launch from Florida in October of next year. So we launch October. I have June of next year. Sorry. Yes, October of next year. That threw me off. The day is first. Yeah, so we'll do it Earth. So Mars, Earth, gravity assist before heading to Jupiter. So we'll swing by the Earth again almost 2 years, about 1.5 years after its launch, and then arrive at Jupiter in 2030. And we'll spend about a year getting configured for our main science phase. So exciting times. And so just to spend the last 15 minutes of my talk, I'd like to focus on my research, looking at geophysical indications of habitability. The main theme of my research is the convergence of geophysics and habitability. So I mentioned both gravity and magnetic field measurements. I won't talk today about seismology, but that's another thing that we can do to understand the interiors of these ocean worlds. And while I'm focused on Europa, this work applies to other moons as well. In fact, Europa Clipper will conduct flybys of Ganymede and Callisto as part of its tour, and we'll do some calibrations there. So I'm excited that some of this work applies at least as much, if not more, to Ganymede and Callisto. So focusing then today on magnetic sounding, since that's something I'm focusing on most recently. This is the study and determination of physical properties using magnetic measurements. And again, this is from flybys, so it's a remote measurement where you're inferring interior properties. So what that inference requires forward models that are based on lab data. So our inference of Europa's ocean conductivity is only as good as our laboratory data and our ability to put those into models that allow us to simulate what's happening in the interior. So we compare suites of forward models with spacecraft measurements to then look at this globally induced field, right? So the applied external field of Jupiter generates this induced field, which is what we measure as we fly by Europa. So from this, it's difficult to know exactly what salts are dissolved in the ocean and how that might vary with depth. These are things that we can hope to figure out, but our goal, the requirement for Europa Clipper, is to do that only in a global sense. So let's just ask what, if anything, we can learn about Europa's habitability from this kind of measurement. And so I mentioned previously the possibility that oxygen is making its way into Europa's ocean due to its generation at the surface and its import into the ocean. So a question we can ask is the ocean oxidized, or is it more reducing? And this is something people have thought about geochemically. This is Misha Zolotov is one of the few geochemists thinking about ocean worlds, been doing that for some time. This is from an LPSC abstract. It's also reproduced in the Europa book from 2009, looking at the modeled molal concentration of ions in the ocean as a function of pH in the ocean, or the fugacity of hydrogen in the ocean. So decreasing pH or higher acidity going to the left. So it's possible that Europa formed as a more reducing body, which would have been led to an ocean dominated by sodium and chlorine in this model. Whereas if oxygen was efficiently imported into the ocean, lowering the pH, that might have solubilized sulfates that were lying around at the bottom of the ocean, and thereby led to an ocean that had a high concentration of magnesium sulfate in the ocean. That's in this model. There have been some more recent models that retain CO2 in higher abundance. That is, the ice is not that efficient at letting CO2 escape. Those oceans then are rich in sulfates from the beginning. But in any case, that's also a more oxidized ocean. So there's this tension between things that might drive the ocean to be more hydrogen-rich, namely seafloor hydrothermalism, and whatever geophysical processes might allow CO2 to be retained or lost. So those two end members then, a sulfate-rich or sodium chloride-rich ocean, can be mapped to simple ocean models. Here I've defined end members of a 10 weight percent or 1 molal magnesium sulfate ocean versus a neutral or basic NaCl, or in this case, I've chosen seawater as the proxy because seawater is well understood. Sorry, it seems that that's not good. Sorry. Okay, great. So I've modeled these oceans using available electrical conductivity data, mainly at 1 bar, though in both cases, actually, I have some constraints on how these vary with pressure. And the reason these are varying with depth in the ocean, shown here in kilometers, sorry, my x-axis label got screwed up somehow. These are varying conductivity with depth because the conductivity is strongly temperature dependent and somewhat pressure dependent. And the temperature varies as a function of depth because of the adiabatic heating over the great depths of the ocean, more so than in Earth's ocean. Although at Europa, only by 4 or 5 degrees or so. So this is something that we need to account for. It changes by quite a lot. But what you can see is that for these modeled oceans and for various assumptions of the ice thickness, here 5, here 30 kilometers of ice thickness, the conductivity is quite different. So these are end members that we might hope to look for in our magnetic field measurements. Moreover, some recent work by my colleague, Julie Castillo-Reger. And again, apologies, this is an older slide. This is now published as of 2022. That work highlighted the outsized effect of CO2 and ammonia, two things that might be present in the ocean, Europa or other ocean worlds. You can see that, so previously I showed around 3 Siemens per meter of conductivity for these different modeled oceans, and the modest proportion of volatiles in the ocean might drive that conductivity up to around 8 Siemens per meter, depending on how efficiently you can retain those volatiles. So something that needs to be accounted for in the future. So the way we account for these things and how we're planning to feed forward models into our analysis of Europa Clipper data is using interior models. So for that purpose, we've constructed the planet profile code, which I developed with my colleagues in MATLAB. It's described in detail in a paper in 2018. Applied it to multiple different ocean worlds. It's recently been converted into Python. This is a paper that's recently out, led by NASA postdoctoral fellow Marshall Szczeciński. And so what we do in this forward modeling framework is we construct radial structure models using available thermodynamic data for ice and for liquids, so that so this code incorporates other open source frameworks, namely the sea freeze code developed by my colleague Baptiste Journeau, and for the rocky part, for seawater, the TEOS-10 used by oceanographers. And so the code asks, based on your ice properties, where does the liquid form? What are the ocean properties? And then it figures out the layer thicknesses based on inputs of the size of the object, the constraints on the gravity that I mentioned earlier, the so-called C over mr squared, or moment of inertia, and knowledge about the temperature at the surface. So independent variables are the assumed composition of the ocean and the thickness of the ice, which we represent as the bottom temperature of the ice. And we can model the density structure based on the thermodynamics. We also model the adiabat in the ocean that's dependent on the thermodynamics. So it's all self-consistent in that way, and thereby dependent on the accuracy of our laboratory data. We model the mantle and core in a similar manner. There are large efforts by geochemists to put together self-consistent thermodynamics of rocks, of arbitrary assemblages of elements, and their accompanying mineralogy. And so my colleague Mohit Melwani Daswani is an expert in this and has taken on the work that I started using this cleverly named PurpleX or Perplex code to generate those frameworks or lookup tables for mineralogy of different objects. So we've applied this to a bunch of different objects. In Marshall Szczeciński's recent paper, he demonstrates how for these different objects we can automatically generate these radial structure models showing where different ice phases and liquids form. So here showing ice 1, liquid water ocean, ice 3, and ice 5 and 6 for Ganymede. And then with decreasing in radial size to Callisto, Titan, Io, Europa, and so on, down to tiny Mimas and Miranda and Enceladus. And so this is now out 2023. Sorry for the old slides. And so yeah, if you download this code and run it in Python, there's a series of test scripts that automatically generate all of these models. And if you're interested, I can show you how to then modify the assumed structures, that is the ice 1 thickness, and some of the other properties like the ocean properties, and figure out how that affects the ocean thickness. So this is a way, in my mind, has been useful for me to develop intuition about how these different bodies might vary in their properties based on their known size and as we imagine what their ocean composition might be like. And so we're actively generating more thermodynamics for different possible ocean compositions, such that we envision modeling thousands of these by the time we get to Europa and being able to statistically look at which are the most likely solutions. So, but focusing on the electrical conductivity that I mentioned, what we can do with Planet Profile then is predict what is the conductivity as a function of depth. So here I'm showing a few more models. I'm showing depth of Europa's hydrosphere. The circles here show where the seafloor is, which is dependent on the composition of the hydrosphere. That is, for the same assumptions of the gravity structure, because the density of the hydrosphere varies with the thickness of the ice, shown here, and the composition of the ocean, which we're allowing to vary for these 4 different compositions of seawater, two for seawater and 2 for magnesium sulfate. And then the temperature structure also causes the density structure to vary. So you see the self-consistent model already demonstrates how lots of different things are co-related. Simply by varying the ice thickness for a fixed composition, we change the temperature structure. That temperature structure then leads to a different conductivity structure. And we can do the same thing for Ganymede, where because the hydrosphere is so much thicker, again, approaching 1,000 kilometers, here showing the high pressure ice is forming. But for this 200 or so kilometer range, 400 kilometers for the warmest oceans, you see that the adiabat is much steeper. And in fact, the temperature of the ocean varies over about 40 degrees. And so that leads to a stronger change in electrical conductivity, which is something we can hope to pick out using magnetic induction. And we've done this for Callisto as well, based on available constraints for the range of possible ocean conditions, where Callisto may have a very thin ocean or even no ocean at all based on current constraints. And so we've worked through the forward modeling of this in a recent paper from Flavio Patricia, again, just published. So lots of progress in recent months. And sorry, these didn't get updated. And so we can use gravity calculations to forward model the properties of Europa that could be measured by Europa Clipper. It's our plan to measure these things. And so for the gravity measurements alone, you get this correspondence between ocean thickness and ice thickness, and you can't decouple that degeneracy. So you say it's in this range somewhere, and there's some likelihood based on the number of samples that show that outcome. So statistically, you might say, great, it's right here. But if you then combine that with magnetic induction, you would then say, well, the most likely constraint in this model simulation is here instead. So ice thickness of 20 kilometers, ocean thickness of 125. Again, this is one large statistical sampling of 1,000 models for a known ocean composition. So that highlights why it's important to have our measurements, our independent measurements of composition from all our remote sensing measurements using Europa Clipper. Just emphasizing how all those things fit together. Great, 1,000 models for one ocean composition. It's not hopeless, but it is a big task. And just to wrap up, I want to mention what I put into my abstract. So people have thought about what Galileo data say about the composition of Europa's ocean. Again, for these end members of sodium chloride, magnesium sulfate. This is from Hand and Chiba 2007. They just took some constraints on conductivity. This is on a log-log scale, conductivity versus concentration. And they looked at what at the time were the expected constraints from Europa's magnetic induction. I would recommend loosening these constraints a little bit. So not much of an upper bound. You're actually limited by the saturation instead. And I would loosen this up just for, because I want to put large error bars on things, such that you could have conductivity and concentration down to 0.1, say. So this is the possible range we could imagine, not entirely constrained. What you want is more fidelity in your magnetic induction measurements, but then that requires more fidelity in your lab data. And so we've done that statistical assessment, and sorry, this got a little screwed up. In brief, here is the amplitude of the magnetic induction signature, and you can ask yourself, what is the corresponding equivalent sensitivity of electrical conductivity that's needed? This is just a derivative of this curve here. So d sigma dB, and then if you have a 1 nanotesla sensitivity in your measurement, which we expect with Europa Clipper, somewhere around there, then the corresponding sensitivity of sigma conductivity is this black curve. And you see that for the lowest range of salinity, 0.18%, you need to get down to 1%. And the few available data, McCleskey for Earth's ocean at 1 bar, they went down to 5 degrees C for a lot of salts over a modest range of concentration. Their uncertainties are getting close, but I would assess that they're a little bit larger, and their data aren't comprehensive to the range that might occur in Europa. And similarly, it's partly inspired by our work. This group in Canada published a couple papers in GRL about sodium chloride and magnesium sulfate at high concentration with high uncertainty that in some cases might actually be just fine for our purposes. But again, sparse coverage in data. So I'm happy that we're embarking on making these measurements ourselves in the simulator for icy world interiors at JPL, and we're building this apparatus to contain our samples and then to conduct impedance spectroscopy to measure the conductivity. So, so with that, I will just stop there with some conclusions about all that we're up to, and happy to take questions for discussion. Thank you.
Thank you so much, Dr. Vance. That was a really fantastic talk about the habitability of icy worlds. We have about 10 minutes remaining. So with that remaining time, I'll relay some questions to you that popped into the Zoom and YouTube chats.
Okay.
So our first question comes from AC in the Zoom chat. AC asks, are there any estimates on dating the impact structures? And I believe this question is referring to the impact craters on Europa.
Yeah, that makes sense. Yeah, so I mentioned impacts on Europa. The constraint on the surface age, the canonical constraint, is less than 200 million years. And so the way this is done for any body in the solar system is by asking what is the expected rate of impacts as a function of size of the impactors. And so that's statistically based and to some extent inferred from the cratering record on Earth's moon, for which we have rock samples from the Apollo missions. And we have this evidence of this so-called late heavy bombardment. And so my colleague at NASA Ames, Kevin Zonley, has published a number of papers on these statistics. So I encourage folks to look at those papers if they're curious. It's really important to point out that that 200 million years is the bulk age of the surface. There are large error bars on that. And it's likely that parts of the ice are older than that.
Awesome, thank you. From the YouTube chat, McCullen Sandora asks, can you elaborate more on the comment you made about the recent progress suggesting that bottom ice may not affect ocean chemistry?
Bottom ice may not affect ocean chemistry. Did I make that comment in this talk? It's something that I might have said, but I don't know if I made it here. So let's see what let me answer the question as I'd like to answer it. If the ice is thin enough on Europa, you might have a conductive interface. That is, water that melts will be less buoyant than the surrounding water, and so will form an insulating layer and might affect the exchange of materials between the ice and ocean. But generally, the ice thickness is going to change over time, if only because these objects are cooling. But in the case of Europa, because tidal dissipation might have increased or decreased over history, you can imagine the ice thickening and thinning, and a thickening ice shell will tend to increase the salinity of the ocean. So the thickness of the ice does affect the ocean composition in a bulk sense, similar to the way that melting glaciers on Earth, melting ice caps are going to make Earth's ocean more dilute, and also can affect the global thermohalian cycles, of which we're only beginning to think in detail in 3 dimensions for icy worlds.
Thank you. And I believe our last question comes from the Zoom chat. Mohammed Abdel Mohisen asks, Dr. Vance, in your model of Europa's strata, you denoted the interior, namely the core, as a metallic core. Do you think that this metallic material may be composed of elements we have yet to discover?
Well, that's a question outside my expertise. The way that we model these cores is predominantly iron, since that's one of the most abundant metals, and we know its properties. I will note that in the study of Earth's core and understanding the redox evolution of Earth's core, mineral physicists continue to ask questions about what materials might be stable in amalgam with the core or intermixed with the metals, including hydrogen, oxygen, nickel, lots of other things. And so we can ask those questions about a core on Europa, but the fidelity of questions that we're asking currently are simply whether or not there is a core. The last thing I'll say about that is that neighboring Ganymede, I didn't mention this before, almost certainly has a molten iron core because Ganymede has its own intrinsic magnetic field, one of only a few objects in the solar system that has its own magnetic field, and the only icy moon that has its own magnetic field.
Great, thank you. So a couple more questions have popped up on YouTube and in Zoom. On YouTube, Rajat Gupta asks, could you please highlight possible applications of machine learning in this area?
Yeah, I'm excited about machine learning and the AI takeover. The community lately has been moving toward a direction of Monte Carlo modeling and Bayesian statistics. So thinking about what is the probabilistic answer instead of the deterministic answer for our studies. These are the kinds of things that might in the future be amenable to happening more rapidly as machine learning can be applied. It's important to caution, though, that developing a model at one planet to give a machine some intuition for how a smaller model set might give you the same result as a larger model set. The assumptions that you make at one planet might not apply to another planet. So it's an area that I think I and my colleagues are interested in moving in, but we need to proceed with caution.
Thank you. We might have just time for one more question. So one that just popped into the chat. Emiliano Mazzei asks, thank you, Professor, for the presentation, for the invitation. I have a question. Who tells us, for example, that the water is not tritiated and might therefore only allow the life of radio-resistant bacteria?
Well, tritiated water, deuterated water is also a problem for life. But tritiated water, I would expect that's something that happens only under nuclear reactions, and that's the kind of thing that I think would only be of concern on Earth recently with nuclear tests. Maybe you're referring to the intense radiation at Europa's surface. I would expect that any such thing would be a small product and not something that would be concentrated. I think the only way you could generate concentrations that would be harmful to life would be through centrifuges, and so that's something you would do in the lab. But not my expertise. This is my off-the-cuff answer.
Great, thank you, Dr. Vance. Unfortunately, we've run out of time, but there are a couple more questions in the YouTube and Zoom chats. But we will have to conclude the September edition of Life RCN Seminar Series. Thank you again, Dr. Vance, for joining us today and giving such an insightful talk on the habitability of icy worlds. And we wish you the best on your work. And before everyone leaves the chat, for those on our mailing list, keep an eye out for our October seminar that we will be announcing soon.
Great, thanks so much. If folks have questions, my email's right here, and have a great day.
Bye.